hope you have at least glanced through the notebook that was shared, the IPYNB file that was shared. Okay, we will do it today. Anyway, exhaustively we will do some examples today. We will have a short introduction to what is the role of linear algebra in machine learning. Okay. Next slide. Okay. So, if you can see here, your attention please. We have a linear system of equations which maybe you are familiar with. We have a few equations here. What we are going to see today is a linear system of equations can be treated as a set of matrices and then you can solve it. What advantage do you have when you put it in the form of matrices? And yesterday we have seen that any problem that we have, let us say you have a data set, that data set, the data points that you have, that will form the variables in this system of equations. Now, the data points will form the coefficients and data points, the parameters x, y, you have m and c, right. So, I will show you an example of how they split into matrices. That the general form is, if you have a system of linear equations like this, then you can put them in matrix form in the following order. You can have x, y, z, the variables as one vector, a matrix, a single column matrix, and the result b . What we tried doing for linear regression was this: we took input data points from the data set. Each data point, we did an operation and then we generated an output, predicted y. The operation was your prediction of y equal to w1 x1 plus w2 x2 plus b. That is what we saw in the class yesterday. So, those operations are put here. So, if you look at this, you can say y equal to f of x, which is nothing but your b naught plus b1 x1, that is mx plus c. If you can extend this, why are we looking at linear algebra at all? Why are we looking at the linear system of equations at all? The first reason is, any number of dimensions, you want to extend these calculations. What we did in terms of linear regression in 2 dimensions, you want to do it and extend it for n dimensions. It's very easy to operate it in terms of vectors and matrices. A matrix is a set of column vectors, or you can treat it as a set of row vectors. So, the set of vectors in a matrix actually form a vector space. Column vectors can form a different vector space, row vectors can form a different vector space. Let us say the dimension of the matrix is 100 cross 5, 100 rows, 5 columns. The vector space would be, if you consider the columns, only 5 vectors. You have only 5 vectors. So, 5 vectors, how many rows? 100 rows. So, you have a 100 dimensional vector space where you have only 5 vectors. Every vector, the number of values in a vector is equal to the dimension of the space. If it is a 2-dimensional vector space, you have an x and y treated as vectors. Every data point is one vector. You know that the dimension of a data point can be more than 2. Therefore, n-dimensional data point means you have an n-dimensional vector. So, if I have 100 data points, I have 100 vectors. Okay? So, that is how we are going to look at machine learning today. If you do operations, vector operations, instead of taking out every data point and doing it, consider all the data points in one shot. Make a matrix, do a matrix operation on that. What you wanted to do to individual elements, individual data points, do it in one shot as a vector. Do it in one shot as a matrix. That is what we are going to use linear algebra for. Linear algebra helps you expand the dimensions, which is very important today. The reason is the amount of data we usually have. Our examples for classroom and academic discussions, we are having very small data set. But imagine the reality. The data set would be, if you are going to take, even if it is just 2 values, a data point has just 2 values, an x and a y, the target value y and the cos, the predictor value x, x1 alone you have. Even if you do that, you take daily for 1 year, you have 365 data points. You take 1 hour once per day, so it is 24 into 365, that many data points, and usually it is just not 2 values in a data point. So, what values you should be having in a data point? That will be explained with an application and examples. As you see through different problems, you can see what should be there in a data point, and that depends on the problem in hand. For example, you want to identify dengue fever, impact of dengue fever in Coimbatore. So, for a year you are watching, let us say, how many patients are coming across different hospitals. Let us consider only one hospital. Okay? All patients coming to that hospital with fever, who is having dengue, okay? Those patients alone you take, or whoever is having fever, they were not identified as dengue, but then that severity was there. So, let us take patients, all of them fever patients in one hospital over a year. The parameters measured for each patient per day, you know, so per day in one hospital, how many patients, fever patients can you expect? For one doctor only you can expect 100. There will be around 5-10 doctors, let us say 10 doctors, let us say 5 doctors only. 5 doctors, 100 patients per person, 500 patients per day. The hospital is capable of doing that, so you have it there, depends on the hospital size also. So, you have 500 patients, 500 data points per day. You do it for 1 year, 500 into 365, remember the size of the data points. Linear algebra is going to be a massive tool to do it very easily. It's very simple. And if you look at what kind of operations you can do in what kind of operations are treated in linear algebra, it is very simple operations. You do vector addition, you do matrix multiplication, you do simplification of matrices, you do factorizing of the matrices, split the matrix into factors. Do you know any one method where how you split a matrix into factors? Any one method by which you can split one matrix into factors? Factorization methods, QR factorization, eigenvalue factorization, right? You have many decompositions possible. You can convert them into 3 different matrices if you create eigenvectors and eigenvalues, and they are all sparse matrices. So, multiplying sparse matrices is going to be very simple operations. So, you reduce the computational time very well, as you can handle a large matrix. A large number of data points at a time you can handle. One matrix you take, do it once. Of course, you are individually doing all the operations. Doing it this way helps you parallelize the operations also. You have 100 data points, 100 different, it's 100 same operations, right? You can split it into different processors. You can give the workload to different processors. So, in a distributed environment or a server environment, high powered, threaded environment, multi-threaded environment, you have multiple cores in a CPU processor. So, you can actually share the workload and do it parallelly. You can do it very fast. So, matrix operations support all of this. So, if you look at it, how is it matricized? Our linear regression equation, the mathematical model for linear regression, how it is M2 and B, M and B, all the M's and B. So, that is your unknown factor. You know Y, you know X. What is X? The data points. X1, X2, X3, X4, you can put all of them in a matrix, that is your X matrix. So, that is given as the input data. In your data point, it is available. The data point also has the target value, the response value, that is the Y. So, the actual Y as well as the input X form the two matrices Y and X. From that, Y equal to XB means, can we not find out B? How do we do it? You can take an inverse, right? You can just see that. Next, it's very easy to convert this. You take an X transpose on both the sides. We are going to make it easy. We are lazy, so we are going to still make it easier. We introduce an X transpose on both the sides. If that is the case, you have X transpose Y equal to X transpose XB. Now, this X transpose X, you take an inverse. Why do we do that? X transpose X is nothing but your X square, right? It's actually your X square. X transpose X, matrix operations, transpose of a matrix is easy to create, and when you do an X transpose X, what you get, the resultant matrix is always a square matrix. It will be a, okay. So, you can see here it is X transpose X B equal to X transpose Y, and then take inverse of this term. So, inverse of this term will say B equal to X transpose X, the whole inverse, into X transpose into Y. So, you have only just the same linear regression what we saw yesterday. We can just implement it in Python in this manner and get the values for M and B. Get the values for M1, M2 and B. I am going to show you that. Very short code, given a data set, you take it, you use this formula, you get your values for M and B in one shot. So, that makes it computationally easier. That is why linear algebra has become important. Using optimization also, we try to find out how can we do or how can we get the values of M and B. See, that was the target in optimization. How do you get the correct value of M and B in such a way that for a given data set, the mathematical model that you have is the best fit. It is decided completely by M and B. How fast do you calculate this M and B is your optimization algorithm. There are a series of optimization algorithms. One of them is gradient descent, and that is what we saw yesterday. We said that using the gradient, that is the derivative, we will update the values of m and b for every iteration. So you can see here, how do you translate? Every data point is actually y1 equal to b0 plus b1 plus, of course, the error value that we get, right? This is what it is, right? Your y prediction is nothing but the actual y, but plus the error. If you include the error, it becomes your actual y. So this is your solution, you need to calculate this. But then in 2 dimensions, can we view what is happening? Into the same thing, you can actually visualize it only in 2 or 3 dimensions, right? So we are simplifying the problem into 2 dimensions to see, we can visually see what it is giving you. The matrix A is nothing but your y equal to x b, right? X is your A matrix. The input values is your A matrix, okay? And y is your target values, y1, y2, y3, the actual y, and b is what we need to find out. So if you see here, the matrix A, which is nothing but the input matrix, input values, you have 2 vectors. 2 vectors and each vector has an xy. Every data point in 2 dimensions has an xy. So that's what you see here. So the matrix will, the determinant of the matrix is actually the area of the matrix, area of the box, the square or the, rectangle, which is formed by these 2 matrices. And you can actually perform these operations to get your B vector. I hope that is understood, right? Y equal to xb, y is known, x is known, you know how to calculate B. So if you look at it, the column vectors of a matrix form a vector space, and if the dimension of the vector space is 100, and if you have 100 vectors, they can actually form what is called as the basis vectors for a vector space. I am not sure if you have heard of what is a basis vector. I can give you an example of basis vectors in 2 dimensions. Your x and your y is the basis vectors for 2 dimensions. Can I have a different x and y? You can have, right? So what is the condition for them to be that axis? They should be orthogonal. So if you have a group of 2 orthogonal vectors, I can treat them as their axis and then plot my Euclidean space vectors, Euclidean points. It's possible. That's what is called a basis. Orthogonal vectors form the basis of a vector space. So if you have a matrix that has 100 orthogonal vectors, all orthogonal to each other, you are actually having a basis for the 100 dimensional vector space. The reference basis, you are actually having one instance of that. So any matrix you take, 100 orthogonal vectors if you have, that will also form another basis for the same vector space. You call it as, if you have 100 dimensions, it should be 100 vectors, right? X and y, you cannot just have y and say I will use it as a reference. You have to have a pair. If it is n dimensions, you should have n vectors. If you have such n vectors, you say that it spans the vector space, it forms the basis of the vector space. So what is the advantage of having a basis? In the x and y dimension, the Euclidean space, any vector, any data point can be written in 2 vector form, ax plus by, right? The vector x and the vector y, some component in vector x, some component in vector y. N dimensions, you have n basis vectors, let us say. Any vector in that space can be written in as a linear combination of all of those basis vectors. That's what linear algebra says. Looking back at our linear regression formula, we said y equal to b naught, or okay, let's just say y equal to b plus m1 x1 plus m2 x2. What are we saying here is m1 and m2 are the coefficients in the x1 and x2, right? So you have a 3-dimensional space with y, x1 and x2 as the basis vectors, and then you have a so you have a linear combination of the basis vectors. You can you can have any matrix work as a basis vector, or any vector with reference to any basis vector. I can select the standard basis vector itself. The standard basis for Euclidean spaces, y equal to 0 for x and x equal to 0 for y, right? You have two equations. Like this, for an n dimensional space you will have n equations. Instead you will have n vectors. Okay, so that is the context in which we are talking. And the column vectors can form a different vector space, row vectors can form a different vector space. If it is a m cross n matrix, m dimensional vector space, n dimensional vector space, you can have both of them, you can treat them separately. And why should we do that? In smaller dimensional vector spaces, we can explore further, computations will be lesser. Higher dimensional vector space, okay, if necessary only we need to go for it. So in terms of vectors, if you look at some of the major operations, or some, I'll just show you only one or two examples of what it will look like in a vector space. If you have two vectors and you want to add them, the vector u is the red line, a parallel line is drawn above, and vector v is your green line. The blue line tells you the addition of these two vectors. Projection, the vector v is here, vector u, okay, the blue color is another vector. You want to project one vector onto the other. So what you get actually is projection of this u plus, I mean the center vector was your vector addition, right? U and v vector. The center, the diagonal vector was your added vector, u plus v. So you try to project it onto the vector v, let us say. This projection is actually got by your dot product. Projection is the idea from where? Vector projection is the idea using which dot products were created. Dot product of two vectors is very important in machine learning because they are very easy. That's what we do most of the time. In linear combinations, we actually do dot product. Dot product of two vectors, let us say a vector A and a vector B, A1, A2, B1, B2. What is the dot product? A1 into B1 plus A2 into B2, right? But this is what we do in our linear regression equation. Therefore, dot products are the way you do in your, that's the way you operate with matrices in linear regression or in linear algebra. But what is the purpose of dot product? One clue I can give you, the data point has a number of values, right? The individual values. So let's say you have 100 data points, but you have x1, x2, x3, x4, 4 values plus the y value, 5 values for each data point. The column x1 across the 100 data points, column x2 across the 100 data points, column x3, x4, these are the 4 values, input values of these data points. These input values, we should now start calling them as the features. Every data point is describing some information, right? It should be done in terms of, you want to take an opinion poll, you don't go and ask somebody, give me your opinion. You will ask specific questions. What do you think this would be like this? How do you think it is like this? Why do you think it is like this? You will have specific questions when you make an opinion poll, and those questions you call them as the features. They form part of your data point. Every question you ask to a person, 10 questions let us say, 10 values form one data point. Another person, another data point. So he will have, so you call those individual values as features. Features are used to describe an object. I will show you an example. Features are the values that form the data point. It could be anything. In general, in machine learning, you will call them as features. So how many features can you have? Can you imagine? How many features can you have in a data point? Is there a restriction? Let's say on the web, in the internet, you want to find out how many people have given an opinion on Modi. Okay? How many followers he has in Twitter? Million followers. I don't know the exact number, but he is the top, right? He has surpassed Obama. So that many people have given opinion. That is the number of data points. Each person, in what all categories he has given, in what all terms he has given an opinion, all of them will form features. Naturally, there is one more aspect to it. Every term in which the opinion is posed, not everybody would have answered. So a data set or a data point will naturally have missing values. I want to consider 100 different aspects in which Modi is evaluated, let us say. Not everybody would have given their answers for 100 different aspects. So if you have a data set that describes the features, then that will always have missing values. So how do you handle these missing values? Will you fill it up or will you ignore it? That's something we will see in our hands-on session. There will be null values. So if you have null values, will you put it as 0 and then continue your operations, sparse matrix, and will you continue your operations? Will that give you sufficient prediction capability for the mathematical model you are training? Will that be sufficient for your training? We will see that in the hands-on session. Okay? So let's say one example. Let's say you have an X column, you have a Y column. How do you do it? Using matrices. You have to find out this X and Y, X into Y, and then you should also find out X square. Do it using vectors. Just do it using vector operations. And once you do that, you get the value for B like this. The dimensions of the matrices should match in order to have matrix multiplication happen. In order to have them happen, the dimensions have to match. So can we look at the second PPT? start looking at examples. Iris dataset is a very standard dataset available. You have a set of flowers, 3 types of flowers. You are going to describe it using 4 features. Each flower, Sneha, can you keep quiet? Or you can go out and talk. The data set has 4 features, that is every data point will have 4 values, the input values, and 1 output. The output will be the type of flower. 3 types of flower is available here, setosa, versicolor and virginica. They have, how do you differentiate them? So if you are given what would be the data points or what will be the features in each of the data points. So the features will be the sepal length, petal length, sepal width and the petal width. Very simple data set for us to start with, and the target will be one of these 3. So if that is the case, what are we doing is, given a set of data points, we are going to learn 3 different types of flowers. Given a new data point, we will identify which type of flower it is. It is a classification problem. Yesterday what we have seen was a prediction problem. Using linear regression we have done prediction. So today we will learn about classification as well as performance of linear regression. In the form of matrix, how do you do linear regression? That's one task. And what is the performance of linear regression? We said that you have to get the best M and W, the minimum error point, right? So different iterations when you go through, how is this error reducing? We will look at an animation of that. What is the accuracy of prediction? As the error decreases, accuracy will increase. You can see that, okay? So in examples, we are going to see all of this. So if you look at it, we are going to today we will introduce ourselves to the library sklearn, Python library sklearn for machine learning. It has some sample data sets. Data sets are nothing but data points. So sample first data set is our iris data set. So in Python, we are going to import iris data set. This is how we do it. And then we load the data into a array. And we will look at what is the size of the array. You will see that the size of the array is 4 features, that is 4 columns, and the number of data points is 150. It's a decent number for us to experiment with. And then look at the number of samples, number of features. Number of samples is your 150, number of features is 4, and the target is 1. And then you can, the target names. When you have a name, how will you put it in numbers? You should give a number to these names. So let us say the first type of flower is treated as 0, second type as 1, and the third type as 2, or 1, 2, 3. Any 3 numbers you have to associate, that will form your Y values. Every data point will have 4 feature values and 1 Y value, which will be either 0, 1 or 2 in this case. 0 means first flower type, 1 is second flower, 2 is third flower type. Animation 1. This is one important thing that we will have to look at. During the training, so in this data set we have 150 data points. What we will do is, we will use 120 data points for training. We will not look at the 30 data points. We will use those 30 data points to test our model. So your training error was used for, perfecting your mathematical model, whereas your testing error will tell you how good the model is. So, the error during training and the error during testing is a matter. During training, as you have more and more data points, the error will come down. During testing, we don't know how your model is going to work. So, tell me whether the testing error should be greater than training error or less than the training error. Should be lesser than the training error, actually speaking, but then testing is something that you have not used for training, that data points. Naturally, more testing, your error is going to slowly increase. It will be slightly higher than your training error. Okay. Number of epochs, it is the number of iterations. As you go through the data points once, twice, thrice, when you go through that, you can see that the training error is very low, whereas the testing error is a red. Animation 2. And if you look at training error and accuracy of prediction, it is the same for classification also, how accurately you are able to classify. This is the relationship you will have. Training error will keep reducing. As it reduces, accuracy will increase. So, the better the training, accuracy of prediction or classification will be better. Though you have a lot of machine learning tasks, we are going to see examples of only prediction and classification, simpler data sets that you can understand, and few explorations like plotting, visualization of the data, visualization of accuracy, visualization of the loss function, a few things we will see. These are the basics that we will be covering. Third one, animation 3. This actually will be your reality. You don't have a smooth curve like that. Usually you will not have a smooth curve. Whenever you do the training, after the first data point, second time the error will go down, third data point the error will go up, fourth data point the error will go down. This is how it will happen. As the number of epochs increase, it goes up and down, it goes up and down. There is these oscillations there in the curve, the loss curve. And it is the same with your testing error as well as the training error. This is how it will be. The reality is this. You can check that. Close it. So, I will show you some examples. You will have to run it. Okay, so run the last one. You will have to start from the beginning. This is a classifier using regression. We were using regression for prediction till now. That's what we learned till now. You can draw a line for classification also. How do we do that? I will show you. But then this classification, is the error decreasing during training? How is the error decreasing during testing as the number of epochs increase? When I have 2 epochs during training and 2 epochs during testing, how is the error changing? And when I have more epochs, how is the error changing during training and during testing? There are many optimization algorithms other than gradient descent. I mean, how quickly you get to your minimum point. There are many algorithms for that. RMS prop is one algorithm, gradient descent is one, bisection methods are one algorithm. So you have a series of algorithms. I can also share a notebook which you can do it offline, you can test it offline, the results of each of these optimization algorithms. Doing it in this kind of environment is very easy to understand because every part of the code you can individually run, and every piece of code what it is actually doing, it's self-explanatory. So that's why you have this IPython, interactive Python compiler, interpreter. Actually it's an interpreter. It's available online, either Google Colab or Azure Notebooks. I'm using Azure Notebooks. Any one of them will work for you. In your own system, if you configure, that should help you test with your own data sets. In case you have your own data set, in the afternoon session, hands-on session, we can help you visualize it. It's over. This one is going. I'll finish it. Oh, okay. But that's okay. Now it is pre-processing, right? As you see this, the next and the last example for the session today, we'll start hands-on after this. Session today would be the classifier. Let us say you are given a few data points with 2 features, x1 and x2, and the target y tells you only 2 classes, 2 types, either 0 or 1. So all values of y would be either 0 or 1 only. And you have x1 column and x2 column, 2 features in each data point. So how will you do classification? Your scatter plot, now it is 3 dimensions, right? x1, x2 and y. If it was linear regression, we would have done x1 and y in 2 dimensions or x2 and y in 2 dimensions. That is the example I have shared yesterday, classroom 1, IPY, NB. But for classifier, what are we going to do is, we are going to consider these 2 features for classification. So we will put x1 in the x-axis, x2 in the y-axis, and then do a scatter plot. We are not going to plot y. For classification, the data points, only the features we are going to plot. So 2 features you have, put it in x direction and y direction, do a scatter plot, color them. Actually, Python matplotlib library allows you to do the plots very colorfully. You can animate them, you can create videos, you can create images. all that is possible. So we can color the data points. All red color data points belong to one class. Still going? Blue color data points is a different class. You will say x1, x2 and y. Using linear regression you will get a y hat. And this y hat minus y, that error we will calculate and we try to minimize that. We use it for prediction. Now during classification what we do is this y will be converted into zeros and ones, right. So your line will not predict the trend in the data. It is going to separate these two data. So how that is possible? We can just see that. You can see 8 epochs. Did it show the animation? Just no, the last part you run again. 7th, yeah, this one you run again. Just keep it down. The number of epochs given is 10. So come down. You can see your first epoch has not happened yet. So you don't see the loss during training and testing. Once you get your first epoch, it will show you the curve. During testing or validation, the orange curve, blue is your training loss. After 2 epochs, you can see that the curves are changing. Up to 5 epochs we can see, and you can test this offline. This notebook we will share, you can test this. I think you can stop. Wait, one more. You can see that the error during testing is increasing, whereas the training error is only slightly increasing. Okay, you can change. Logistic regression, classification regression. So this is your data points. You have around 17 data points, x1, x2, and you look at the y's, they are all zeros and ones. This is a binary classifier. You have only 2 groups of data, and your y values will tell which group the data point belongs to. You can run it. So if you plot it, you can just run it down. If the plots are available, you can just run it down. So this is your scatter plot that shows the data points. You can see that in x-axis we have x2, and in x1, and y-axis we have x2, the first column and the second column. This is the function, or the y, once you do a prediction, y prediction, right, actual values of y are zeros and ones. But when you use the regression mathematical model and calculate, the y hat will not be zeros and ones. It will have a different value. You will use a function called the sigmoid function. Using that function, you will transform the y values into something between 0 and 1. I hope you understand that. Let us say first data point, x1 value is 1, x2 value is 4, and y value is 0. What is the equation you use? Y is equal to m1 x1 plus m2 x2 plus b. Using this, if you calculate the y hat, that will come to some 12 or 14, let us say. Your initial m1 and m2 and b you have assumed, and then the y hat you get is 12 point something. Now whether it is 0 or 1, how will you know? So that has to be transformed. Every y predicted value has to be transformed using a function, and the formula that will be used is 1 by 1 plus e power minus y. So the y value will be put in the exponential negative, e power minus y. So 12.3, let us say you got as the answer, it will be 1 by, it will be converted to this new value, which is y double dash. Let us say y double dash is equal to 1 by 1 plus e to the power minus y hat. That will be e to the power minus 12.3. This new value will always be between 0 and 1. That is the speciality of this function. So all your y predicted values will be between 0 and 1, and you can decide 0.5 and above as 1, below 0.5 as 0. So that will be your classification. So this is your sigmoid function, you can test that, and let us say come down, for that data set we are doing a regression, we are calculating y, and you see that the loss reduces with the number of iterations. Come down. If you plot the line, now you will get it like this. This is how you will get. So this actually works as a classifier. What are you trying to, you don't have to even look at the plot, you look at the y hat, the predicted y hat values. It will be between 0 and 1. You translate it and make it as 1 and 0, right? If it is this range, you say it is a class 0, and if it is this range, you say class 1. You can decide the threshold. So that way, if you draw the line, now you will get it like this. It acts as a classifier. For small data sets, this actually gives good results. It's also used very popularly in neural networks. You can stop here. Iris scatter. Plot iris scatter. Scatter. So the last one is the iris example that we discussed. It's three classes. The other method you call it as logistic regression. It's called as logistic regression method when you use, and the function that we have used 1 by 1 plus e power minus y hat is the sigmoid function. We use a sigmoid function to transform the data and create classes for the data. You can see the iris data set has got, the scatter plot is given here. Now you want to classify them, group them. You can come down. That's the last. You can see they have been colored as three different classes. They have been identified using the classifiers. There are a series of classifiers. In the hands-on session, we will teach you how to select one of them and do your classification. Logistic regression, you can give the name logistic regression using the library function and then do the classification. Using linear regression or regression itself, different types of regressions are available. You can use one of them and then use for prediction. And classifiers, as you learnt yesterday, support vector machine is one classifier. Even if you do not know the internals of the classifier, naive Bayes is a classifier. So you have a series of classifiers, how to select them, how do you do performance comparison for a given data set across the classifiers. So those are things that you will learn today. And with this, you can go up a little bit. You can see that this is the code, literally some 10 lines of code if you are using the library functions for doing classification. The classification is done using support vector machines. So you can have multiple classes. Any number of classes you can classify the data into. Okay. So what we have seen, all examples have been supervised learning. So one example of unsupervised learning during the hands-on session in the afternoon, I will tell you, which is nothing but your k-means. So that I will have you do it in your notebooks in the afternoon. Okay. Thank you.